Okay, the camera seems to be pointing off somewhere in... Okay, whatever. Okay, well, I have to move through things quickly so we can get our lunch. Now, unlike the morning lecture, this is going to be less theoretical. And the goal is to talk to you about the TAHMO project that Tadessa and I are involved in. So if you want, I don't know that we'll have time to go through the notebook, but you can download this notebook. And I'll give the URL again at the end. But Tadessa has a GitHub site, github.com/tadiz DSA 2018. And you want to download the whole project. It's not too big, but there's some CSV files and a Python notebook, and then you'll be able to hopefully replicate what I've done in these slides. You're going to also put it on the thumb drive and the. Okay. Great. Okay, so the plan is I'm going to give an overview of the TAHMO project itself, and then the challenge of sensor network quality control, and then we have this exercise on the notebook for you to do. So TAHMO. So the motivation for the TAHMO project is that Africa is very poorly sensed. This map over here, it's a little small, is from the World Meteorological Organization, and it has a dot for each weather station that regularly sends data to WMO. WMO is part of the United Nations. It's one of the specialized scientific agencies, and they set standards for world weather data and so on. So what we see is that in South America and in Africa and also bits of Indonesia, we have very poor weather sensing. Very few ground stations are reporting. And you might say, well, we have satellites, we have other ways, but we'll argue and show you some data that we really need ground observations to provide better input to global weather models and build better weather forecasts. One of the consequences of having poor sensing is actually reduced agricultural productivity, right? So in most parts of Africa, you cannot purchase crop insurance if you're a farmer. And if you can't purchase crop insurance, then what you do is you plant your plants very far apart. So if you look at the maize fields here, the maize plants are fairly well separated. And the reason is if the rains are low, those plants will still survive because each plant has a lot of soil around it and it can pull the moisture out of that. But if you look in the US and Europe, for instance, they plant their maize plants really close together, like 2 inches apart. It's just incredible. Because they have crop insurance and they know if the rain is insufficient and the field is destroyed, they'll get their money back and they will survive financially to the next year. So the main motivation behind TAHMO is if we can provide data, that will lead to things like crop insurance and other benefits. In the United States, it's estimated that our weather network is worth something like $30 billion to the economy. So data is money. And so the goal of TAHMO as a project is to make Africa the best sensed continent by taking advantage of the revolutions that we're seeing in sensor network technology, like the stuff that you're using from ARM. This is super cool. We're not quite that sophisticated with our weather network. I'll show you our stations in a moment. But our goal is to deploy a network of 20,000 weather stations and give complete coverage to all of sub-Saharan Africa at about a 30-kilometer spacing among the stations. We have about 500 stations deployed now. And I guess the other important thing here is we have created a nonprofit company, but it needs to be self-sustaining, right? Like so many development projects fail unless we can come up with a business model that will at least be a break-even model for this company. So do we need ground stations? So what I've got here is a scatter plot of this is for a particular ground station that's at South Tetu Girls High School here in Kenya. And on the horizontal axis is the predicted rain according to the GPM data product, which is there is a constellation of satellites in orbit around the Earth, and they give pretty much complete coverage of the globe, and they try to estimate precipitation from that. And they estimate to, I believe, 10-kilometer cells. And so we took the cell that this girls' school is in, where we have a TAHMO station, and the vertical axis, there's one point plotted for each day in the years 2016 and 2017. Was it both years or something? And it shows that, for instance, right here we have the amount of precipitation measured by a TAHMO station was something like 52 millimeters, and according to GPM was only 20 millimeters. You can't read those axes at all. But we can see there are a lot of cases where TAHMO reported 0 and GPM reported greater than 0. Those could be TAHMO station failures, actually. If the rain gauge gets plugged, we might report 0 when it did rain. Here are cases where TAHMO reported rain and GPM reported 0. And we also have some pretty crazy points like this one up here, where TAHMO reported a huge amount of precipitation at this one station, but GPM, perhaps because rain can be extremely local in terms of its extent. And so it could be that this is true, that at this particular station we had a very large amount of rain, and yet averaged over a 10-kilometer cell, maybe not so much. So the R squared for this regression line is 0.22, so at least it's positive, but we're only explaining 22% of the variance by trying to predict TAHMO's precipitation report from the GPM report. So this is what we've seen pretty much all over, is that the satellite data, the satellites can measure the droplets in the air, but it's difficult for them to tell whether the drops are reaching the ground, I think. I think that's part of the problem. So our business plan. We have been negotiating memoranda of understanding, MOUs, with each country in sub-Saharan Africa. And we're able to raise funds through gifts and grants mostly to develop and deploy the weather stations. The real challenge is operating them, and the hope is that we can operate them by selling the data to things like insurance companies and commodities traders, financial industry. And we actually we're trying to come up with other interesting things we could use to do the data that would be something that could be of value financially to support the network. We give free access, of course, to the government in each country. Data about a country belongs to that country, and to education and research institutions. So here's a list of the countries for which we have MOUs, and some are, our first one was with Kenya, and we were then able to use that as a model to go to other countries and show them. We've got a pretty good coverage in both East and West Africa, and we are close on 5 more countries. In terms of the overall financial plan, we estimate that it's going to cost about $40 million to deploy the network, and we're a long way from that. And it costs, the station itself costs about $1,500 right now. That's 10 times less than a standard WMO station costs, but we would still like to try to make it even cheaper. But then it costs an additional $500 to get them shipped here and get them installed in the field. But then the operating cost, this is the tough one, is $600 per station per year. So that's our current estimate. So probably $12 million we need to have in revenue per year. The weather data market, my colleague John Selker, who's the head of the whole project, estimates that in Africa it could be $40 billion a year. Maybe that, Africa is very large, and that would be scaling up the value of data in the US. But certainly it could be very big, much bigger than the amount of money we need to run the network. So our current status is we have more than 500 stations deployed. We've had funding from the United States government, the UN, the EU. IBM bought 333 stations for us. And we also have something we call the school-to-school program that I'll discuss. So technology. This is a Generation 1 weather station. So it had 3 moving parts, including a traditional anemometer, right, with the spinning cups and the wind gauge. and 5 components and a lot of cables. And so we're very happy with our Gen 3 station, which has no cables. Well, there's 1 cable. And only 2 components. I mean, there's a cable that comes from here down to here, right? I don't know why it says there's, well, anyway. But this is what the weather station looks like. There's an open cone in the top, so precipitation goes into the top, goes through a cone, and forms up into water droplets that then are measured electrically. So one of our big goals was no moving parts. So nothing, because moving parts break and stop moving. And so this traditional tipping bucket rain gauge is notorious for breaking. And so we're using this thing, but we do have a moving part still, and it is the water itself as it goes through the system. And so if you get leaves or bugs or fungus growing in the cone, then it can become blocked. So they call these automated weather stations, but they're really semi-automated because really you need a human being to go like once a week or once every 2 weeks and clean the station. There's a solar radiation sensor on top. It gets dirty. Sometimes a strong rainstorm will clean it for us. There's an ultrasonic weather wind speed measurement, thermometers, and so on. I guess I have a full list of all the sensors over here. Yeah, so it's solar power with a 6-month reserve battery. So we have a little tiny solar cell on the data logger. This is the data logger, and here's its cellular antenna. So we're using cellular data networks to do the data upload. And that's working pretty well for us, but some of our stations are pretty remote, and they end up running their batteries down trying to get a cellular signal. And so, so that's a challenge for us, and maybe we can explore some of the technology that we're using here. This LoRa networking may be an alternative for us. We have a GPS on there, which was primarily there as a theft deterrent, because we could track the station, find my weather station instead of find my phone. But we also use that to get the exact location and elevation of the station, which is very important. Temperature, relative humidity, wind speed, drip count rain, solar radiation, a barometer, a lightning detector, and we have 5 open sensor ports to put in things like the solar, the soil, moisture, temperature, pollution, all kinds of other sensors can go on there. We generally have been following the strategy of placing our stations at schools. So we have developed a program where we recruit a teacher who's willing to monitor and clean the station, and ideally use the data from the station in their classes. And so we provide curriculum materials, suggested things that they can do with the data. And so you can use it to teach basic statistics and plotting graphs. And of course, you can use it in physics class and things like this. And so that's been very successful. We have a lot of, we came with lesson plans that were developed in the US, threw them away and completely redid them to local people, not us, but to really match the needs of the schools here. So, and we do have a school-to-school program. The original concept, it was a fundraising concept that we could get a school in Europe or North America to buy a station for a school in Africa, and they would get a station too, and then the 2 schools could have a kind of cross-cultural exchange and compare data and compare, culture. It isn't really working very well, but yes.
Are you giving the US or Europe school one similar? It feels like you don't need to spend as much money on the one in the US. I know it's a bit stingy.
We're giving them the same station.
Oh, wow.
Yeah. Well, they're buying that station, and they're buying 2 stations, and they get to keep 1. But they're richer generally. But the real issue, I think, is the overhead of all the communication stuff. It really doesn't pay off. But the idea of having teachers be our sort of station keepers, and that's working really well. And I think, as those lesson plans and so on get improved, teachers themselves create a Slack channel, and they take it and do cool stuff with it, and the main thing is they have access to the data so they can think of all kinds of things. I mean, you know, success always involves unleashing other people's creativity, not trying to do it ourselves. So here's the current status. So the countries in red have at least 20 stations in them. So we're doing pretty well here, and of course in East Africa. We have 5 stations in Madagascar, but no local representatives, so it's very expensive for us right now. We have to fly someone over there to, yes? Our goal is to do the whole place. Why should we not, yeah. Yeah. Well, we did start in Kenya and Ghana as our first sort of foci, because we had people, local people there already engaged in the project, and our CEO is from Kenya, I believe, right? Or is he Ghanaian? He's Ghanaian. Okay. I don't know. You know, the weather, in terms of providing value, weather station value, geographic coverage is really important. But it is true that the Kenyan Meteorological Organization is extremely enthusiastic, and we have stations now in all but 2 of the counties. We have more than 100 stations in Kenya, so it is our best instrumented country. I think there's a map here next that shows, I don't know if you can see, but at least in here we have a large number of stations, and also in Uganda. We're planning to put 80 stations, more stations into Tanzania this coming year. And we're negotiating with the Rwanda and Burundi, because we have some funding, I think, from the UN to do a sort of, you know, all of Lake Victoria kind of understanding. And you can go to our website, which is tahmo.org, and look at the whole station map. Yes? My understanding is, but I'm not 100% sure about this, but I think the idea is that, right, that you have access to all the data if you have a station, because again, there's a really strong network effect with weather data that having access to only the data on your own station doesn't tell you very much. But if you can look at the data for the whole country or something like this, then you get a much better, you know, much more value out of it. The weather doesn't really respect political boundaries, but there are various, you know, every country, we have differences in the MOUs, so sometimes the data first goes to the meteorological agency in that country and then to us. It can be very complicated. Yes. Right. I don't know the answer, but I can put you in contact with our business development people, and they can give you a lot more of the details. Yeah, I'm the data scientist, right? So I don't really. This is the first time I've ever talked about the business. Obviously, I need to learn more about it. Okay, well, why data quality control? And the answer is, of course, that sensors fail once they're deployed. I mean, if we could just keep these sensors indoors in the laboratory, there'd be no problem, but for some reason we want to stick them out and expose them to the weather. So I've already mentioned some of the problems: solar radiation, the wind sensors get dirty or blocked, the rain gauge becomes obstructed, but also these stations just find novel ways to fail. So for instance, here's a weather station where some ants decided to lay eggs all inside the station, inside the data logger. Here's a case where wasps decided that this would be a good place to live, right, where our ultrasonic wind sensors. What? How? No, these are one-off cases. Might be quite common. Yeah, it might require a redesign. I don't know. Yeah, it's definitely. We have made some improvements over the years. This is a Generation 2 station, I think. Well, what do we want to do with data quality? So here's data from actually a temporary weather network in Switzerland. and you can see they were having some really severe problems with spikiness and flat lines, complete dropout of the data signal at some times. These were temperatures, so each of these wiggles is a day. And so what you would like is to flag every data value that you think is invalid, right? That's been because the sensor is damaged in some way. And then another thing you might want to do is to produce an imputation, that is to fill in and predict what would have been observed if the station hadn't failed. That, of course, takes us beyond data to what's called a data product, right, where we're using some sort of model, in this case a statistical model, to fill in the missing values. And this was work, I had, my previous PhD student on this was a guy named Ethan Derezinski, and we had a paper in the ACM Transactions on Sensor Networks back in 2011. So, what are the yes, sir?
Sorry, must be so many. It's just because the air pollution thing is so many similarities. One thing we're already doing is all our data in the air pollution sensors is already on ThinkSpeak, but one thing I'm aware of is we definitely need to calibrate the oxygen.
Right.
And I'm worried about even releasing raw data publicly because people then might just use it without knowing. Like,
right.
just ignoring the fact that there's a
Yeah, I mean, the best practice for weather networks is they only release quality controlled data. Typically, or they may release the raw signals, but with a flag, right, attached to it that says, we believe this is bad, or we believe this is suspect, or we think it's good. So that's kind of the usual thing. How is it done in most networks today? Well, if a network is small, so we have something called a long-term ecological research station at our university. They have 3 main weather stations and about 10 more. They just plot the data and look at it. So some person just does the kind of thing we were just looking at, in Python or R, and finds problems. But of course, that only works if you have time. The next step up is known as complex quality control, and this is what's used in the United States in our National Weather Service networks. And then there's something called probabilistic quality control, which is used by the weather balloons networks. But all of these require large amounts of time, and the TAHMO network is going to be much larger than any existing weather station network if we really succeed in our 20,000 stations. So we need something that's, well, okay, maybe not fully automated, but something that is more automated than any previous approach. So complex quality control is basically you write a set of rules. And the rules, if the rules are violated, then you flag that data point. So one kind of rule might be that the temperature cannot increase by more than 12 degrees in 5 minutes or something like that. So basically, it's called a step test. So if we take the temperature at time t+1 and we record on a 5-minute interval, not 20 seconds or whatever you're doing with the greenhouse, that's just madness. But even 5 minutes is maybe faster than we need. Some weather networks that do it at 15-minute intervals. But we can look at the t+1, meaning t+5 minutes minus the current time, and that should be less than some threshold theta. And you could have a downward step test also. Flip this around, and it should be less than some other, theta 2 or theta 3 or whatever. Typically, they include a flatline test, right? Because a very common failure mode is that the sensor just starts reading a constant value, particularly in cold climates when the sensor freezes in some position in the wintertime, or if it just goes offline. And so you can say, well, how many consecutive steps can the signal be unchanged before we should raise an alarm, right? Or over the course of 10 hours, there should be a certain amount of variance in the signal. This is a physical thing we're measuring. It should be changing. Then there's the buddy test. If you have 2 identical sensors on the same station or nearby, you can compare them, and they should not be too different from one another. And on and on. So, you can write, typical systems have 20, 30, 40 rules in them. The main problem with this is that there are no underlying principles, so it's hard to know if you've got a complete set of rules. That's not even really well defined. And they tend to consider just one variable at a time, which, very often there's strong correlations between the different variables. I'll talk in a moment about relative humidity and temperature. But when the temperature goes up, the relative humidity generally drops. So they are negatively correlated. If you're looking at only a single sensor, you can't take advantage of those correlations. And the rules, as a piece of software, rules are hard to maintain. But the advantages are it's very practical. It's easy to add new rules, hard to maintain them once you've added them, but it's easy to add them. And it doesn't require any fancy model of the signal, so it works out of the box from day one. You can start doing things. Whereas if you use machine learning data science techniques, we need the station to be deployed for 3 months or something till we have a really good statistical sample of its behavior in order to use a density estimation type technique. But if you do have probabilistic models, then you can use probabilistic quality control. And so the idea here is that we're going to have, I really should have had I think I have a thing later. Let's pull up this. The basic idea is that we're going to say, so suppose we have some sensor reading down here, and we have like the temperature, and then we introduce a state variable, ST, which is that sensor healthy or is it broken? Is it okay or is it broken? And so the idea is to have two probability distributions. What is the probability distribution over the sensor reading when the sensor is working? And what's the probability distribution when the sensor is broken? And so if there's something like this, this might be the probability of temperature at a particular moment in time. It might be have a pretty focused distribution here, if the sensor is working correctly. And if it's broken, we might use some very broad distribution that says, well, if it's broken, almost anything could be reported, right? And then if we observe a value like 3, according to the broken distribution, it has a low density, but according to the working distribution, it's much higher density. So it's much more likely to be working correctly, right? Whereas if we observe a value like 5 here, it's the probability that that is a working sensor is much lower than that it's broken. So you basically do probabilistic reasoning to ask. Of course, you can also have a prior probability distribution, P of S, on just the probability that it's working versus broken. Most sensors are working, so that would make this distribution much more likely. And so then we model, it's very much like the models we described this morning, but now we want to use Bayes' theorem and calculate the probability that the sensor is working given the observed reading. And so we can do our diagnosis that way. The big challenge in this is modeling the broken distribution, right? Basically, we're setting it up as a kind of supervised learning problem. We have training examples of working sensors and training examples of broken sensors. It's easy to model the distribution when the sensors are working because we have tons of data for that case. But broken sensors, despite all my pictures, are actually pretty rare, much more rare. And so it's hard to get training data for these. And also, sensors break in novel ways. And so it's very hard to predict what sensor readings you'll get when, for instance, ants have invaded your data logger. What does the data look like in those cases? It could depend a lot on exactly where the wasps position themselves as to what the observed things. So it's going to be very hard to model. So that's why we want, a typical thing that's done is to use what Chris Williams calls the junk bucket distribution. We just make a guess about what the distribution will be, and I've used a uniform distribution here as the broken distribution. That's really just equivalent to setting a threshold, right? That says if the likelihood according to the working distribution is above that level, then it's working. Otherwise, it's broken. And so this is hard to do well, and it's hard to do when you have multiple sensors. Much harder to figure out how to set that threshold. So our idea that we're pursuing is to use anomaly detection methods. So suppose we could assign an anomaly score to each observation, such that scores near 0 are normal and scores maybe greater than 0.5 are anomalous or something like that. Big scores, anomalous. And then we'd like to learn a model of the anomaly scores themselves instead of the raw signals. So we want to model if the sensor is working, what should the anomaly score distribution be like? If the sensor is broken, what should the anomaly score be like? And our hope is that modeling the distribution of anomaly scores will be much easier than modeling the raw sensor readings. That's the That's the key claim that our scientific hypothesis from a machine learning standpoint. So I already put this up. The idea is that we observe the sensor reading, we compute the anomaly score, and then we ask what value of the state variable would maximize the probability of the observation, best explain the observation. And so that's going to be the probability of the sensor being broken a priori, and then the probability of the anomaly score conditioned on that. So there are cool things you can do if you're doing probabilistic modeling, right? So we can say, well, this is our two variables at time t. We have two variables at the time t plus 1, t plus 2, t plus 3. And we can say, well, if a sensor is working at time t, it's likely to still be working at time t plus 1. So we can model this idea of persistence. And of course, if it's broken at time t, it's very likely to still be broken at time t plus 1 because sensors rarely heal themselves. I mean, I did mention the solar radiation sensor, and a good rain can wash it off. So that is an example of a self-healing sensor. But in general, unless a technician visits the site and cleans it, a sensor that's broken will stay broken. Another cool thing we can do, right, is to look at joint distributions among variables. So here's data from the state of Oklahoma in the US for one weather station, Weber. And on this axis is the relative humidity, and on this axis is the temperature. This is for July 2009, measured, I think, at 15-minute intervals. And so you can see there's a very strong negative correlation here that as the temperature goes up, the relative humidity drops. And the cool thing about that is, suppose that we had an observation that said, well, it's 20 degrees outside, but 40% relative humidity, so that would be a point right here. Now, if we were only looking at it from the point of view of, is 20 degrees a reasonable temperature for a sensor to return? Well, yes. We have lots of 20 degrees over here. And is 40% humidity a reasonable number to report? Well, sure, we have lots of 40% relative humidities. But the combination of them has zero probability of happening, right? It's just way outside of the observed range. So that's why we can, the importance of exploiting, modeling and exploiting these correlations can really improve our accuracy in finding broken sensors. So to do that, we have to set up, our model looks like this. We have the state of the thermometer, the state of the relative humidity sensor, and the two of them together influence an anomaly score that's applied to the combination of the temperature and the relative humidity at time t plus 1, and so on. So you can see our probabilistic model is growing more and more complicated. And what we do in general is what we call a multi-view approach. So, you know, I guess if you thought about it only mathematically, if you have a network of sensors, then you have this gigantic joint probability distribution over every sensor at every site at every time forever. And you could just model that as a giant density estimation problem over those millions of variables. But of course, that's not practical. So what you need to do is, do you have a question? No. We form sort of small views in the sense of in a database, you know how there's this idea of a view that you select a subsample of your variables, perhaps only the schools within a certain range, whatever. That's called a view when you look at some subset of the data. And so we can have a view for a single sensor over the most recent k time steps and assign that an anomaly score. We can look at an anomaly score over the rate of change. That's like a step test in complex quality control. We can look at the difference between the values at two different weather stations, or we can even make a regression model that takes the sensor readings at k neighboring stations and uses them to try to predict what the reading should be at our station and looks at the anomaly score of that difference. And this is one of the things we'll talk about next. So we want to combine all of these different views to then do diagnosis. So our diagnostic model looks kind of like this. Time is going from left to right. And these are the states of let's just say a weather station that just has a thermometer and a relative humidity sensor. So these are the states of the thermometer. The thermometer is sensor 1, and it's at time 0, 1, 2, 3, 4. And this is sensor 2, is the relative humidity, 0, 1, 2, 3, and so on. This is a view that corresponds to a reading for the thermometer and the relative humidity sensor together. This is a view that is the three most recent readings of temperature, the three most recent readings of relative humidity, and the A's are all anomaly score. And so we might, so that's what it looks like. So runtime quality control basically means you assemble all the incoming data into the view tuples, that are for each of those view nodes, compute the anomaly scores for each tuple, and then do probabilistic inference to try to find what set of sensor state values, capital S, would maximize the probability of the sensor states given the anomaly scores that we observe. Of course, we can't wait for a whole year to go by, and so we have a sort of online approach to doing this. So these, the light gray cells, let's suppose that we've observed the data values for times 0, 1, and 2. Then that means we can evaluate the anomaly score for this 0 through 2 range, and for this one here. And of course, we have each of these single time step things. And based on that, we're going to try to make inferences about these two sensor state variables. So we say the data time is time 2, but the diagnosis time is time 0. And so we do the diagnosis, and then we say, well, we think this one's working, and maybe we think this one's working. So we commit to that, and we're not going to change our minds later, even if we see later evidence. Then we advance the clock, and now we see the observations up to time 3. So data time is 3, and now we try to infer the values of these two state variables, and so on, going across time. Yes, sir?
You don't have the lines, the arrows between the state variables?
I lost them, yes. They should be there.
They were, okay, cool.
They should be there. Yeah, I noticed. Yeah. So how do we compute the anomaly scores? Well, we could just point to this morning's lecture. We could do some sort of joint model of temperature and relative humidity. But it turns out that this is a lot more complicated. Like each month it's different because it depends on the day of the year and the amount of water in the atmosphere and various other things. We could try time series models, and Tedessa spent, I don't know, maybe almost a whole year on time series models for this. But basically, weather is very complicated, right? So there's an annual cycle, right, where it's warmer some parts of the year and cooler other parts of the year, based on the length of the days and so on. There's a daily cycle, so it's cooler at night and warmer in the day. And then as weather systems come through, like the rain that we're having today, that changes things too in a very kind of chaotic way. So it's really hard to fit good time series models to the weather. So our current, and we'll see a month from now, maybe I'll change my mind, but our current approach is to try to build regression models from a nearby station. And the idea is that if we have two stations that are close together, then they will tend to experience all of these effects together. If it's hot time, they'll both be hot. If it's cold, they'll both be cold, and so on. And so that way we don't have to model all of those different sources of variability. We can just compare two neighboring stations. So we're going to do a regression-based density estimation of the kind I described this morning. So we want to fit a regression model that, say, predicts the temperature at location L as some beta naught plus beta 1 times the temperature at some other location L prime. And as I mentioned this morning, ordinary least squares regression assumes that this response variable actually has a normal distribution or a Gaussian distribution whose mean is determined by this formula and whose variance can be calculated as the variance of our residuals. And then we can use the negative log density as our anomaly score. Well, so how well does this work for temperature? So using data from the US, we have partners with something called the Oklahoma Mesonet. In the US, the state of Oklahoma has the most violent weather. So they also have the best weather network and the best weather people, all the latest technology. So here's one station, Boise, and another station called Kent. And you can see that you have a tremendously good fit of the temperature at Boise and the temperature at Kent. And these were all taken at, I think, 0 universal time for each day of 2009. And the regression equation looks something like this. The temperature at Kent is 0.73 plus 0.96 times the temperature at Boise. So it's a little warmer at Kent than it is at Boise, on average, by 0.7 of a degree. Well, how good is the assumption of the normal distribution? One way to check that is with something called a QQ plot. And I don't know if you've ever seen these before, but the basic idea is we're going to plot our data points in which we have this so-called standardized residuals and the theoretical quantities. So explaining this better, on the x-axis, we take all of our residuals from the model, so our prediction errors, how different they are, right? And we fit a normal distribution to them. So we calculate the mean and the variance. And then according to that, we can calculate the quantile of each point. That is the probability that the temperature would be less than or equal to that observed temperature. And so we plot that on the x-axis. And on the y-axis, we can also just say, well, if we sort them from, in ascending order, the point that is at the midway point is the 50th percent quantile, and the one that's at 25% of the way through is the 25th percent quantile, and so on. So we can also plot them just empirically. And so if the data are normally distributed, the quantile is calculated from fitting a normal distribution to the data, and the quantiles just from looking at the empirical distribution, those should line up. But in fact what we see, and so they should lie in this line, this dotted line. But in fact what we see is the classic sign of heavy tails, that things do weird stuff at the ends. And so we can also do a kernel density estimate of the looking at our residuals. And so this red line is what the normal, a Gaussian fitted to our prediction residuals would be. And then the black line is this kernel density estimate. So you can see the kernel density estimate is a lot tighter near the true value, but it also has heavier tails out here. And so that's why it's not really a Gaussian distribution. So I use the R density function for this, but in the Python notebook you have, there's a scikit-learn version of this too. So now we come to precipitation. So temperature, this really works well. It's great. But precipitation is our nightmare variable. If it weren't the most important variable we were measuring, we would just give up on it. But it turns out precipitation is really the single most important weather variable, right? But precipitation is 0 most of the time. But when precipitation comes, it can be very strong and very spiky. So it is totally not a Gaussian distribution, right? The average precipitation is somewhere up here, right? But if you draw a line like that, that doesn't look anything like the real data. So what can we do? What we do is we model it as a mixture of two components. So we talked about mixture distributions this morning. This one is a little bit of a weird mixture because with some probability P0, the rain is just 0. So that is a probability statement at a single point. We would say it has an impulse density at a particular point. And then with probability 1 minus P0, we will have an amount of rain that depends on, that will have some probability distribution. What's the amount of rain conditioned on it being greater than 0? We find actually that predicting the log of the amount of rain seems to deal with the fact that it's very bursty. And so we're using a log transform on that. So here's a kernel density estimate for the log of the rain when the rain is not 0. And so I don't know whether this is reasonable or not, but it shows a fairly large bandwidth, 0.6. This looks a little bit like my plot this morning when the bandwidth is too big, so I don't know if this is quite the right thing. But in any case, recall this morning that how do you do density estimation when you're also doing transformations of the variables? In this case, if we let g of log of x be our density estimator for the amount of rain, we want to have f of x the density estimate for the rain itself, not the log of rain. And it turns out we can get that by taking the density assigned to the log of the amount of rain and dividing by x itself. And again, that comes from the general rule that says that we need to multiply by the absolute value of the Jacobian of the transformation. In this case, the transformation is a scalar transformation, so the Jacobian is just the derivative, and the derivative of log is 1 over x if we're using the natural log, and so that's why we get this formula here. So it's very simple and cool. So here's what our combined model looks like with if the rain is equal as a density to score densities. If the rain is 0, then we output a minus log of P naught as our anomaly score. And if the rain is greater than 0, then we output negative the log of 1 minus P naught times our fitted density over the log of rain divided by the amount of rain. So, so that would be for a single site if we were just modeling the rain at one place, because at that one place we know whether it rained or not, and we're just scoring it. But as I mentioned, we're really interested in predicting the rain at one station using the rain at another station. So here's the rain, the amount of precipitation at Boise and the amount of rain at Kent. And again, we see that they're not super well correlated with each other. Although they tend to agree more that when it's 0 at one place, it is 0 at the other. But it doesn't look super promising. But what we're going to do is now make a conditional mixture model, right? So we're going to, we need, there are the two components. So there's the probability of rain versus not rain. And so we can set up a logistic regression function. And I know you played a little bit with logistic regression in the warm-up Python notebook. But the idea is that in logistic regression, we have a binary response, did it rain or not, and we model that as the log of the odds ratio, probability of rain divided by probability of no rain, and we say that's equal to a linear function, a plus b times the amount of rain at the other site. And then for the second component, so that models the does it rain or not, and the second component is then if it does rain, how much does it rain? And here we could try to take model of the log of the amount of rain as a linear regression, and maybe use a kernel density estimator over the residual noise. Unfortunately, this doesn't quite work because, well, anyway, I'm getting ahead of myself. So to do this, to fit that model, we convert the Kent rain to 0, 1, just round it to 0, 1, and then we fit the logistic regression model, and then this is what the fit looks like. So what I'm showing here is the actual observations of whether it rained or not, and then these zeros are the predicted probability of it raining. And so we get sort of the standard sigmoidal shape, more or less, and we see that these places where it rained, we predict that it's not raining with very much probability, but we do really well when it's raining a lot at Boise. We predict that with probability 1, it will be raining at Kent. So it's hard to plot against a 0, 1 variable. So, so a common thing we do often is to plot an ROC curve. And I don't know how many of you know about a receiver operator characteristic curve. So relatively foreign concept. So right, we can think about the basic idea is to plot. We could set a threshold on our 0, 1 prediction, right? We're out of the logistic regression model, we're getting this estimated probability of rain at a place. And we could set a threshold here and say, if the model ever predicts with more than, say, 0.1 probability that it's going to rain, we predict yes, rain. Or we could set a threshold up here at 0.9 and say, we will only predict rain if the model says 0.9 rain. Now, if we set the threshold down here, we will never, if we set it at 0, we'll never predict any rain at all. So we'll have a lot of false negatives where it rained and we were wrong. But if we set it up here, I'm getting this backwards, aren't I? If we set it down here, we predict it rains all the time. And so we'll have a lot of false positive predictions. If we set it up here, we'll have a lot of false negative predictions. And so you can map out a curve where you plot on this axis the fraction of points that you predicted incorrectly, the fraction of negatives that you incorrectly predicted as positive. That's called the false positive rate. And here we can predict we can put the true positive rate, so the fraction of rainy days that we got right. And if we set our threshold really high, we won't predict any rainy days, and so we won't make any false positives, and we won't have any true positives either. And as we change our threshold, we can map out this curve, which is called an ROC curve. And of course, eventually, we've got our threshold so low that we predict that it's always raining, so we get all the positives right, but we also have a false positive rate of 100% or 1.0. And so people are very interested in the area under this curve. The perfect ROC curve would go straight up here and then straight across here, and it would have an area under the ROC curve of 1. And random guessing would have an area under the ROC curve of 0.5, just totally random guessing, which would correspond to a diagonal line here. And occasionally we see methods that do worse than random guessing, and they would be below that diagonal line. So the area under the curve is 0.84, which is actually pretty good. Another way of saying that is that if I randomly chose a day when it was raining and randomly chose a day when it was not raining and asked the model, which one do you think is more likely, it would correctly, with probability 0.8397, it would correctly assign a higher probability to the rainy day than to the dry day. So we'd like that to be 1. It's 0.85. That still surprised me that it was that large. Okay, but it's not perfect. And if it's not perfect, then although we can use this, we have our model for P1, the probability that it's raining. It won't be perfect, and therefore it's very hard to train the model for how much rain we're going to get using only the non-zero values of rain, because there will be some errors. So what we're going to do instead is we're going to add a small epsilon to each of the rain values so that we can take the logarithm of it. See, the difficulty here is really taking the log of 0. Because we're going to get some days wrong, when we try to fit our amount of rain model, and we try to take the log of 0, we're going to get negative infinity, and it's not going to work. So a standard trick is to add a small quantity like 0.1 to each of the observed rain values, and then do a linear regression that says, well, we're going to predict the log of the rain plus epsilon as being equal to C plus D times the log of the rain at the other station plus epsilon. And the other thing is, for each training example, we can employ a weight on it, which is how well the 0-1 model, what it predicted as the probability of rain. And then what we want to do is find C and D that minimize the squared error of this, but putting more weight on the days when we think it's raining and less weight on the days when we think it's not raining. And so we end up, after you do the transformations, we can get the probability of rain originally is equal to the probability assigned to the log of the rain plus epsilon divided by rain plus epsilon. So again, it's very cool that you can use the derivative to figure out how to correct for having made this additive transformation in addition to the log transformation. It all just works. So here's what our quantitative rain predictions look like. These are the zeros down here, but it's not too bad on a log scale. There's a lot of variance, so we can't predict it with great precision, but at least it looks like it's got the right shape. If you move back to the original scale, it looks like this. And here are our residuals on a log scale. If we're doing ordinary linear regression, we would expect a Gaussian spread. Instead, of course, the kernel density estimate shows that we're doing very accurately here, but we do have heavy tails. The bandwidth is a bit smaller here. And here's what the anomaly scores look like. So here's the actual rain at Kent for each day of the year. So you can see the rain is kind of bursty. And here is the minus log probability scores assigned by our mixture model. And you can see that the highest anomaly score was at a value of about 10, which corresponded to one of these readings here, which is kind of surprising. Whereas this very large reading here was evidently not surprising, because there must have been a very large reading also at Boise that predicted that. So, of course, it's very hard to evaluate these. It turns out that according to the Oklahoma people, there were no failures at this weather station this whole year. So one thing we do is Tedessa has developed some simulators that will insert fake failures into the data. So we will wipe out, in this case, one thing we can do is just say, well, the rain gauge actually reported 0, even though these were the true values here. So we're simulating a totally plugged up rain gauge. And then we can ask, well, what anomaly score gets assigned to that? Well, the first day and the last day, it actually assigns a lower anomaly scores than it did with the regular model. But in the middle day, it assigns a very high, like anomaly score of 22, which is twice the score of any of the days, the normal days. So that's very reassuring. And in the notebook, you get a chance to reproduce this, but using Kenyan data instead of Oklahoma data, and using Python instead of R. So the results will be much better, presumably. And so just to summarize then, TAHMO is creating a weather station network of really unprecedented size. And we need a QC quality control method that can scale and be as automated as possible. Existing quality control methods are either rule-based and ad hoc or probabilistic, but require some hacks to get them to work. And so we're hoping that we have a more principled approach. It still requires defining multiple views, which takes a lot of domain knowledge. But then we fit an anomaly detector to each view, and then we can do probabilistic quality control, which is very principled, I think. We can do diagnostic reasoning then to figure out which sensors are broken. This need for diagnostic reasoning is a bit of a, is a sort of, in some senses, unfortunate. But when you have highly correlated sensors, like when I showed you that example of the relative humidity and the temperature, if you get a point that is anomalous, then you don't know whether it was the thermometer that was broken or the relative humidity sensor that was broken. All you know is that this combination is impossible. So so we need to have another view that, say, compares the temperature sensor to another thermometer and the relative humidity sensor to another relative humidity sensor, and then do our probabilistic reasoning over all of those to figure out which sensor is the one that's broken. So it's really, if we embrace the goal of looking at the joint distribution over multiple sensors, then we also have to deal with this diagnostic phase where we try to do root cause analysis and figure out which sensor is really the ones that are broken. In a traditional weather system, system using these old techniques, they would have just flagged them both and left it to a human being to figure it out. And so we're trying to automate that. And this is actually also very closely related to the challenge of explainable artificial intelligence, right? We have a system, and it's not enough to just say, something strange happened on this day. You'd really like to say, something strange happened on this day, and I think it's the rain gauge that's broken. And so that's the real challenge. Okay, so again, okay, I think I said all these things. You can get Tadessa's notebook and the supporting files from this GitHub account or from various other means, I guess. And what you'll do is you'll fit the probabilistic precipitation model for up to 3 stations in Kenya. And then you have the opportunity to insert fake sensor failures and see how well we can detect those sensor failures. And so I think a challenge is, setting a threshold, what value of theta could detect all of the fake failures while minimizing the false alarms. In data science terms, we call that finding the right value of theta that gives us 100% recall. That means we find all of the true failures, and then subject to that maximizes the precision, or minimizes the number of false alarms. And so at that point, how bad are the false alarms? How much extra work is the human analyst, the weather person, going to have to do to deal with those false alarms? So those are the kinds of questions. How am I doing for time? Did I finish in time for lunch?
Yes.
Okay, great.
So I think we'll have lunch.
Okay.
For just half an hour, and we are back. We'll just do the exercise before the mic starts.
Okay, terrific.
Half an hour activity
Okay,
for lunch.
eat quickly.
Yeah, eat quickly, and then when you come back, we'll go through the tutorial before my
Okay. Yeah, we don't have to do the exercise if there's not time. Oh, it's good? Okay.
I just need to get it.
It will certainly use everything that was in the.
Yeah, well, I'll put it onto the, is that on the one which is Roger? This has the.